So, hello everyone, this is Luboš Pirkl from CFD Support, and I'd like to welcome you to the webinar about CAE simulations, specifically about turbomachinery benchmarks we did in the past here at CFD Support. As you know, we've recently delivered a new comprehensive engineering simulation environment called TCAE, which is based on open source and which has substantial value cost ratio. And it will be our pleasure to show it to you in today's webinar. I hope everything is working fine. We are running live at the moment, so in case of any technical problems, it happens all the time. So in case of any technical problems, feel free to contact us and we will gladly answer all your questions, comments, and whatever you need. The webinar is being recorded and the recording will be made later publicly available, typically on our YouTube channel, but we will send you a notification where you can find it. And yeah, I think maybe it's time to move on. So please let me quickly introduce the webinar speakers of today's webinar. Well, yeah, it will be just me. So it's just me today. My name is Luboš Pirkl. My current job at CFD Support at the moment is telling the world about us. And I'll be happy to host this webinar just myself. The webinar is going to take about an hour. In the first part, there will be a general introduction when I'll show you I'll give you a general introduction about what's going on and what's on the table. In the second part, I would say in the main part, I will show you a couple of benchmarks and a couple of examples of what we did with special accent of comparisons of the results with the measurement data. And finally, in the last part of the webinar, there will be a Q&A session dedicated to your questions and our answers, or my answers. So feel free to ask your questions anytime during the webinar. Some questions will be answered right away in the webinar, and the rest of the answers will be answered later via email. But you can be sure all the questions will be answered, and no one will be left behind, because your answers, your questions are very, very important to us, and your feedback is very important to us. So, yeah, just a super quick introduction to our company. Our company is called CFD Support. It was founded in 2009. It's located in Prague, Czech Republic, and at CFD Support we deal with engineering simulations at all levels, and of course primarily we focus on the development of CAE software with a very high added value for its users. It's definitely high-end software. It's high-end software with several verticals. I will speak about it a little bit later in this webinar. And our clients are CAE professionals who know well what they want. We are obsessed with the accuracy. That's what is today's webinar about. Accuracy is our highest priority, and besides accuracy, it's definitely a focus on automation, repeatability, and application-tailored solutions. We don't believe in general purpose codes. Specifically, we don't believe that any particular software can accurately simulate everything, or that anyone can simulate anything. We do believe that any successful project is a result of focus, skills, experience, patience, and dedication. We believe in open source. Especially, we believe in a combination of open source and professional support. So far, we have invested more than 30 many years of focused team development on top of open source to deliver this professional simulation tools, and that's why we are being picked. We have a very strong team of developers. Despite the COVID pandemic raging around the world, we keep working very hard, and so shortly after the new year, you can look forward to another TCAE version release once again with a lot of new capabilities. But now here's what's on the table at the moment. So TCAE is a comprehensive CAE engineering simulation environment. It has successfully merged the benefits of open source with the benefits of commercial codes. So due to the open source nature, TCAE is unlimited. It's extremely flexible, and due to the commercial code nature, it has a graphical interface, it has professional technical support, it's robust, it's accurate, it's automated, and it's well tested. And I would say altogether it's ready for simulations in the industry. This is how the graphical interface looks like at the moment. The user can do here pretty everything from the simulation setup and the simulation run to the detailed post-processing of the results. Besides this graphical interface, the user can also run TCAE in the batch mode, of course, and TCAE can be, for example, run by another software, or it can be used inside a bigger simulation chain if needed. The new version 20.9 has more than 144 different little projects in it. Some of them were just a small issues, some of them were nightmares, but what's even more important, TCAE is very comprehensive. It is a simulation environment rather than just a CFD code as it used to be in the past. It includes in itself 48 open source packages. To name the most important ones, it's, for example, an OpenFOAM version distributed via openfoam.org or ParaView or Calculix or NetGen, for example, and also many other useful tools, useful open source tools to support the engineering simulations. You can imagine how much work their authors have spent on their development. And on top of that, we here at CFD Support, we have spent more than 30 many years to deliver this TCAE environment for you to take the benefit of it. So as already mentioned, TCAE has a modular character. It consists of software modules that can be combined together according to the project needs. Those vertical modules are individual modules, and they can work as a standalone tool. So the user can pick those. The user can choose those modules that he needs. So if needed, the user can combine those modules with many other software pieces available in the market. So, for example, the user can, I don't know, create a geometry in CF Turbo, make the mesh in the module TMesh, and run the simulation in TCFD. Or, for example, the mesh can be created in cases, meshed in Grid Pro, and the simulation can be run in TCFD, and structural analysis can be done in TFEA. Or the mesh can be created in pointwise and simulation and in TCFD or whatever. So the total number of combinations is almost infinite. TCAE has strong integration ability. It has been from the beginning developed in a way to fit any existing workflow, no matter what it is combined with. No matter if it is combined with commercial codes or in-house codes or with another open source code, because it has strong interfaces and it's very flexible. So in a typical enterprise, the engineers usually have some existing workflow already, and TCAE is capable of fitting into it no matter what design tool is used, no matter what CAD tool is used, no matter what meshing system is used. TCAE is still here to fit any workflow, to do the simulation, deliver the results for the user's judgment, and the user can decide what to do next. I personally like this puzzle analogy, so I will show more puzzle pictures later in the webinar, and you can follow it and think about it, how it fits your personal workflow. Yeah, so TCAE is definitely very flexible. It's ready for very complex workflows and simulations at any product design stage. It's ready for optimization loops. It's ready for quick simulations. It's ready for big simulations. It's ready for cloud computing, and it's ready for all, or I would say for many other trends going on out there. So yeah, the real tutorials are available. The best practice in the real tutorials is available. And yeah, the tutorials are based on the real projects we did in the past, so they're definitely very, very close to what's working, what has been tested. Okay, so one of the biggest benefits of TCAE is it's unlimited. It's completely unlimited on the number of its users. It's unlimited on the number of the sessions, jobs, and cores it's used. It's unlimited on the number of hardware installations, so it definitely gives a good scaling potential to it or into the game. Yeah, the user can use the resources to the fullest, and that's good. TCAE is very accurate. It's like I mentioned, it's definitely not a general purpose code. It has a clear focus. It's always aimed on particular applications and particular simulations that allows TCAE to be accurate. So the best field, it's been proven for years. It's turbomachinery simulations. It's also perfect for external aerodynamics. It's definitely not a general purpose code. It's focused code. And yeah, here at CFD Support, we are obsessed with the accuracy. We think it matters. It's very important, and we do our best to prove it all the time. So later in the webinar, I will show you. And yeah, we definitely believe that CAE or CFD or FEA is those are sciences which deserve care. It deserve patience, experience, dedication, and it's all about the skills. So yeah, a couple of benchmarks are available. I will show you later. Yeah, TCAE is from the beginning developed in a way to fit modern engineering workflows. It's fully automated. That's very important. This automation brings a huge effectivity into the game. TCAE can be used either as a black box, so the user can just put the data in. TCAE does its job, and the user picks the results at the end, or TCAE can be used as a highly sophisticated software where all the options are open. And I would say that the beauty of TCAE is that it's the user who decides how deep to dive into the details, or not at all. Okay, so well, we believe in the importance of the technical support. The technical support is definitely part of the game. It's coded in our DNA, and it's also coded in the name of our company. After all, for more than 10 years, we have supported the engineers in achieving their goals. We are obsessed with professional technical support. We have a special process for it, which is powered by the OS ticket system. Yeah, TCAE is natively compiled for Windows and Linux operating systems. There is no need for any virtual systems at all. The engineering workflow is exactly the same on both Windows and Linux systems. Our typical user does the case setup and the first quick tests in Windows, and then she moves with TCAE on Linux clusters to use it on multiple cores to fully benefit from the fact that TCAE is unlimited on the number of users, jobs, and cores and everything. So HPC is definitely about Linux, and smaller simulations are definitely or many times run in Windows, as you know. Yeah, sure. Yeah, and in the batch mode, of course. About the meshes, TCAE includes a fully automated meshing system based on SnappyHex mesh and NetGen, and also the external meshes created in another external software can be loaded in it. So we always leave this, I would call it mesh decision, up to the user. So some users prefer automated meshing, the other users prefer external meshes. That's fair enough, and we fully respect that. It's ready for that, for sure. TCAE has strong post-processing. Every simulation that is executed in TCAE has its own HTML or PDF report with the results. So volume fields are visualized in ParaView. The integral results are saved in CSV files for later post-processing, or all those plots and everything is written down in the report. So the report is very important part of all of it. Okay, as you know, no software is ever finished. TCAE remains under continual development. The development is users driven. So we continually gather the requirements from the TCAE users. We evaluate them and we keep adding them into the new version releases. We use special system for code development in a team which is called GitLab. I guess maybe you know it, or it's very popular at the moment for code development in a team. So that's what we use, and TCAE is definitely an open-ended system of simulation modules. It will always keep its modularity. Regarding this, we have two ways of thinking. It's the horizontal development, which is adding new tools, new software modules, and the complexity, and also the vertical development, which is adding new applications, new capabilities, and high-tech methods for those existing modules. Okay, I'm approaching the main part of the webinar, so yeah, I'll just mention a few main applications which is TCAE good for and encouraged to be used for. So TCAE core business has always been turbomachinery simulations. Yeah, TCAE can simulate many kinds of machines, all the sizes, both radial and axial machines, both compressible and incompressible fluid flows. The typical use is, for example, the pumps or fans and blowers. TCAE is definitely very good for hydro turbines. It's being used for compressors and turbochargers, and also wind turbines. That's what has been proven by many years. Yeah, later what had worked so well in the turbomachinery field, we decided to extend for external aerodynamics to simulate cars or the aircraft. Nowadays, TCAE can simulate also the internal aerodynamics, for example, all kinds of valves or water valves, hydraulic valves, or various exhaust manifolds or intakes, or the piping systems. TCAE shows also fantastic performance for simulating the water propellers, ship hydrodynamics, and the air propellers, or even wind load acting on the surface of the building. And last year, TCAE was extended by capabilities of heat transfer and then human comfort simulations, for example. Okay, so as already mentioned, we are obsessed with accuracy. In the past, we did a lot of benchmarks with our clients. Basically, all of the clients want to see some proof that it works on his machine with and on compared with his measurements. So we do this benchmarking with almost every new customer. So we have compared the simulation with the measurements data in many times with the measurements on real existing machines. From some clients, we have received a permission to show the comparisons publicly, and we are happy to show you. So I have prepared a couple of examples. I have 9 examples today, and in this webinar, I will give you reasonably general information about what has been done. I'm not going to torture you too much with the details, but the good news is most of the details are available in the public reports, so feel free to ask about the details, or you can find them on our website. Okay, so I will start with the first one. The first example I would like to show you or to share with you is the CFD benchmark validation of France's hydro turbine. This project was made together with company Hidroenergia, which is a hydro turbine manufacturing company from Brazil. This project is pretty unique because the real existing hydropower turbine, which is really installed and working in Minas Gerais in Brazil, it was physically measured, and the measurement data were compared with the data from the CFD simulation by TCFD. The particular goal of this benchmark was to compare the turbine efficiency and power with the TCFD simulation. So here below you can see the workflow scheme. So the original CAD model was cleaned and prepared for the simulation in Salome. The computational mesh was created in SnappyHex mesh, and the simulation was executed in TCFD. On the right hand side you can see the comparison of the measurements and the simulation results. So as you can see, the individual points along the complete turbine characteristics, and as you can see, the results agreement was very good, and everybody is happy, and the details of this benchmark are definitely available in the public report in PDF, so you can find it on our website, or you can request it. I will gladly send it to you. Okay, so the second benchmark we did is again, it was a collaboration with ZVVZ Machinery. It's the fan maker from the Czech Republic. We simulated together a centrifugal fan. In this particular benchmark, the engineers were interested in the accuracy of TCFD as usual. Everybody is interested in it. The simulation of this particular centrifugal fan was actually pretty challenging because of quite wide impeller and quite low pressure difference versus flow rate ratio. So the measurement results were again available, and we could compare the simulation results with the measurement results. Below you can see the workflow scheme. The original geometry was designed in ZVVZ in-house code. The geometry was created from the parameters using the TCAE module. The mesh was created in TMesh using SnappyHex mesh, and the simulation was run in TCFD. So we made both steady state and transient simulations, and on the right hand side you can see the comparison of the results. It's the efficiency versus flow rate and total pressure versus flow rate. As you can see, the agreement of the results is very good. It was well above the expectations, and again, the details are available in the public part of the report in PDF. The next example I have today is the Potsdam propeller benchmark. It's a famous ship propeller test case. It has been extensively measured in the SVA Potsdam laboratory in Germany. The measurement data is publicly available, so as well as other CFD codes results. So there is really a lot of public data available about this test case. Below you can see the workflow scheme. It's pretty simple. In this case, the mesh was created in pointwise, and it was loaded in TCFD, and to run the simulation on the right hand side, you can see the main results. It's the thrust coefficient, the torque coefficient, and the efficiency versus the advance ratio. The agreement of the simulation results with this measurement results is outstanding. In fact, we couldn't wish it any better. And again, the details of this benchmark are available in the public report in PDF, and also the test case is available, so anyone can run the simulation and again to check it himself. The next example is benchmark on compressible fluid flow. We did this benchmark in collaboration with CZ, the Czech company who produces turbochargers. It's a simulation of the compressor side of the turbocharger. The compressor impeller is 55 millimeters in radius, so it's quite large. And this turbocharger is, it's used in big diesel engines. Below you can see the workflow scheme again. The original geometry was designed in a CZ in-house code. Then the model was cleaned in Salome. In this specific case, we created also the simulation mesh in Salome, and the simulation was performed in TCFD. The measurement results and also one commercial code results are available for comparison. We simulated complete compressor characteristics. There were 3 speed lines at 60, 80, and 90,000 RPM. And again, on the right hand side, you can see the comparison of the results, the efficiency, and the pressure ratio. As you can see, the agreement of the results is pretty good. And again, the details of this benchmark are available in the public report in PDF. The next example is special. It's a detailed benchmark focused on parallel scaling. As you know, the scalability is one of the most important features of any CFD code. Any modern CFD is, for any modern CFD code, it's critical to show linear speed up with increasing the number of simulation cores, especially for unlimited CFD codes like TCFD is. It's very crucial. The scalability is critical because its users can use their hardware resources to the fullest. So scalability definitely is very important. So we made a detailed study of TCFD parallel scaling. The tested case was France's hydro turbine. The scaling results were amazing. On the right hand side, you can see that the major figures. You can see the speed up is almost linear, and the parallel efficiency is very high on our little cluster we have here at CFD support. This study clearly proves that TCFD has very high scaling efficiency, and it's great for large simulations on multiple processors. And again, the details of this benchmark, the hardware and the setup and everything is available in the PDF. Okay, the next example is a complex external aerodynamics. It's a study of the Spitfire, legendary aircraft from World War II. We found the original, or we found the CAT model and of the aircraft, and also we found the original measurement data for it to compare it with the simulation results. So this case is quite specific because it's a mix of the external aerodynamics with the turbomachinery aerodynamics. So we did the simulation. You can see the results again on the right hand side. The agreement with the results was good. The model was cleaned in FreeCAD. The mesh was created in SnappyHex mesh, and the simulation was executed in TCFD. And again, the details of this benchmark are available in the public PDF. Yeah, Ahmed body. This is a classical study that presents the benchmark validation of CFD simulation of this famous external aerodynamics test case, which is called the Ahmed body. We did the simulation using TCFD. Ahmed body, as you know, is a generic body, a car body. It's basically a simplified car model, and the flow of the air around the Ahmed body captures all the essential flow features around an automobile. The aim of the benchmark validation was to evaluate the TCFD results and compare the results with the measurement data. And the particular goals of this benchmark was to compare the drag coefficient, to compare the velocity profiles, and also velocity field, and the time averaged wake structure behind the model. So these four features were followed in detail, and the CFD results were compared to the experimental results from the wind tunnel, which are publicly available. So we did it, and the results were perfect. And again, the details of this benchmark are available in the public report in PDF. The second last benchmark I'd like to share with you today is a bicycle wheel optimization study we did. This study was I have to say that this study was completely created by our collaborator Streamline Cycling from the UK, and initially there was an initial validation done comparing the wind tunnel calculated drag and lift coefficient of the NACA profile 2212, and it was compared with CFD results. And later a small section of the bicycle rim was tested and optimized using the cases and TCFD software all together in a joint workflow. And again, the results were compared with the wind tunnel testing. So the cases was used to generate the geometry, and the TCFD was used to make the simulations. Okay, once again, the details are available in a separate PDF report. Okay, in the last example I'd like to share with you today, it's called beam ball benchmark. It was especially created to validate specifically the fluid structure interaction between the flow and solid. This study is unique because the exact solution can be evaluated, it can be calculated analytically, and the analytical solution can be compared with the simulation with the simulation results. So the particular goal of this study is to investigate and compare the deformation of a beam. There's a fixed beam, a beam which is fixed on the floor with a ball at its end, and this beam with the ball is stressed by the airflow flowing around it. And so we did such a case. It's the CAD model was created in Salome. The mesh was created in T-mesh using SnappyHex mesh, and the CFD simulation was executed in TCFD. And this fluid structure interaction part and the finite element analysis was solved in the software module TFEA. And the results are very reasonable, and once again all the derivations and calculations and all the details are again available in the benchmark PDF. So feel free to take a look in the PDF how all it was done, because it's definitely here not the space for the details. Okay, so that it was those couple of examples I had prepared for today, and now it's time to answer some of your questions. So feel free to ask your questions. I will pick some important questions that I find interesting for all the audience, so people can hear it here publicly, and then you can be sure all the questions will be answered. So feel free to ask your questions. Okay, so yeah. So this one is this. Okay, here's a typical question. About the turbulence model. So Martin is asking if what turbulence model has been used for the simulations, and if there is what turbulence models are available. So basically, I can say that you can in general, you can use any turbines model which is available in OpenFOAM. In TCAE, we have I would say 5 or 6 turbines model. You can pick right away. Just use it. And if you need some other which is not listed, then you can certainly use a special scripting in Python, which is we call it user-defined function, and you can load the model manually, like from the script. So that's of no problem to use any custom or any other OpenFOAM turbines model. Okay. So what else? What else we have here? Yeah, here's a couple of very specific questions. But that will be easier to answer, or it will be more polite to answer them individually. Dale Smith is asking, is it possible to apply periodic boundaries for simulation of propellers and turbomachinery? Also, do have test cases of gas turbine components? Yes, of course. Yes. Periodic segments is I would say it's compulsory for axial machines. So yeah, we did many of them. Maybe I can very quickly switch somewhere to the. Okay, I would need to leave this, but we did a lot of axial stuff. Sure, absolutely yes. Dale, what's funny, it's we started our journey on large steam turbines for Doosan Skoda Power. It's former Czech companies Skoda Power, which was later acquired by Korean Doosan. So yes, definitely periodic segments, periodic boundaries, and all this stuff, and also axial turbines are definitely very important part of what we do. Okay, so I'll go back to, I'm sorry, yeah, I need to, what do I do? Click present again. Okay. So yes, certainly. How can I apply this simulation to fish? Yes. Okay. No. Let's discuss this in a separate discussion via email. Fishery circulating system. No. Let's discuss this somewhere else. Yeah. About the meshing. Maybe you noticed that I mentioned that TCAE is very flexible about meshing. So you can either use automated system, which is for CFD. It's based on SnappyHex mesh, so very robust automated meshing system. We have very good results with it. So you can use automated meshing for CFD, SnappyHex mesh for FEA simulations, you can use a NetGen. They're automated and they work. They're part of the solution. Or you can load the meshes in CGNS format, or in OpenFOAM format, or in MSH Fluent format. So you can load your own meshes. We are absolutely fine with that. So it's always up to the user. So either automated meshing is available, or the external meshes can be loaded. So that's always up to you. Yeah, I'll answer this later. I don't know what's gotten code, so I'll answer this via separate email. I'll Google it and come with the answer. Can the grid data be exported? No, yeah. I'll come with this later. Can this perform transient thermal related problems? Okay, so it definitely can simulate transient. It definitely can simulate compressible and incompressible. About for compressible flows, the temperature is involved, but this would need to be discussed in details. Okay. So we have a couple of very specific questions, so we will answer them later. I need to check it with the team. The last question: is there a mesh limit? No, there is no mesh limit. So I have seen simulations with this with hundreds of millions cells, which is quite large. So no, there are no limitations on this. Okay, so I think maybe it's time to conclude. Anyway, feel free to ask your questions anytime. We are happy to help. We are happy to support you. It's our job, and it's a pleasure for us. So I'm personally never tired speaking about CFD, speaking about market, speaking about business. So feel free to get in touch. We will gladly we will do our best to support you. Okay, so I will finish with this last logo slide. You can see here a few of those who already share our visions with us. Many others are already on their way. There are a lot of who didn't make it to this picture. So I apologize. I should make a couple of other pictures. Anyway, any one of you is welcome in our family. Any one of you is welcome to join us on our journey. The bigger we are, the stronger we are. It will be our greatest pleasure if you join us along the way. Okay, so this will be it. This will be really it from today's webinar. I hope you have got some inspiration. Feel free to ask any questions. Feel free to get in touch. We will definitely follow all your questions, and it's our job and a pleasure. And I think this is it. So, okay, thank you for your attention. Feel free to get in touch. And this is it for now. Bye-bye.